Hello, students. Going over a brief little bit of the homework from 4.2. Again, this is the topic on prime numbers. So kind of determining whether something is prime. And let's kind of see. Let's jump over here to 4.2. Okay, so it's kind of a factor tree. I think I assigned, let's see here, 1 through 13, 17, and 18. So 1 through 13, 17, and 18. So 1 through 13. It's basically that first page. So some prime factorizations, fundamental theorem of arithmetic, prime factorizations, and then 17 and 18. So kind of a couple little word problems there. All right. Let's see here. So let's jump back over, maybe take a look at a couple of these and make sure. Determine which are primes, determine what is the greatest prime to be considered to test something, use a factor tree. Okay, so a lot of different steps. Basically, it's all revolving around the prime numbers. So doing A or B should be just fine. So maybe let's do a couple of these as we go. Let's see here. So again, if you're kind of finding a factor tree, if you have all the numbers here, they're kind of saying, hey, can you fill in the missing numbers? So if they've already got the primes at the bottom, just work your way back up. Remember, all of these are related to multiplication. So again, to get here, this is basically, this line is saying 3 times 55. And so 3 times 55, 150 plus 15 gives you 165. And then this is saying 2 times 165, so this would be 330. And if you want to check yourself, it should be 2 times 3 times 5 times 11. Okay, so there's a kind of a quick way to go through and do those. A lot of these I think aren't going to be too, well, hopefully not too time consuming because, well, they're meant to be just about primes. Now, again, if it's been a while since you've done things like factoring numbers, then it might take a little bit longer. But let's take a look at a couple more of these and see if we can't knock some of these out. So let me jump to some white paste. The next one says use a factor tree, find the prime factorizations. Okay, so we'll do a couple of these along the way. Let's see here. Yeah, let's hit a few of these. Okay. So I'm not going to do every problem, but might as well try a couple of these. So I'll do B. It looks like it's kind of in the middle. So prime factorization, look for things that you can pick up quickly. And it does say use a factor tree. So 2475, last digit is a 5. So I pick that up. But the last 2 digits is 75, which means there's definitely a 25 in here. Okay. So now 25 goes in. Remember, the other number that goes in is if I just do the division. So if I do 2475 and divide by 25, and what we get over here is 99. Okay. Another way to look at this number, if you did happen to see it, is it's 2500 minus 25. So that's another way to kind of look at it and say, So this is basically saying if you factor the 25 out, 25 times 100 minus 1, which is 99. So it does match up perfectly. And then just continue breaking this down. 25 is 5 times 5. 99, let's see here. Why don't I do 3 times 33, I guess? And 33 would be 3 times 11. So there we go. It says use the factor tree to find the prime factorization. So I want to make sure I list the prime factorization as 3 squared. That takes care of those two. Then I have a 5 squared. That would be these two over here. And finally, an 11. And you could leave 11 by itself. You could write 11 to the first power. It means the same thing, but this would be our prime factorization. Now they do the same thing down below, like for the number 251. Once you start getting into exponents, the factor tree is really not that helpful anymore. So why don't we jump in and do at least one of these other ones where it has nothing to do with a factor tree, right? Okay, so I'm gonna do blue this time. Okay, so why don't we take any one of these? Let's pick. Maybe I'll do like A and let's see here. Normally people are like, don't do the easy ones. Okay, I'll jump down. We'll do A and D. Let's take a look at A and D. So here for A, I have 1 times 2 times 3 times 4 times 5 times 6 times 7. Somebody really enjoyed this one, writing this one out, right? All right, so first off, I'm just going to kind of underline the primes I already have. I have a 2, 3, a 5, and a 7, so I don't need to factor those. The 4 here would be a 2 times 2. The 6 here is 2 times 3. So notice I'm not breaking the whole thing into these little pieces along the way. I'm finding all of the factors. This would be 2 times 4, I guess, which is 2 times 2. Finding all the factors, and then I'm just going to bring them all together at the end. All right, so there they are. Now it's all split up. So what would this equal? Let's start with our smallest prime, which is 2, and then just count all of them. 1, 2, 3, 4, 5, 6, 7, and that's it. So I have 2 to the 7th. Next up, I'm going to choose all my 3s. So there's 1, 3, 1, 2, 3, 4. Okay, so that's 3 to the 4th. Next up would be my 5s. I just have one of those. And lastly would be 7s. And so I just have one of those. Now, again, you could write this as 7 to the 1st, and you could write this as 5 to the 1st if you wanted to. You don't have to, because this is the prime factorization. Okay. Woohoo! Oh, let's see here. 100 to the 10th power. Man, somebody really enjoyed the heck out of this one. But it turns out if you look at it, 100 to the 10th power is the same as 10 squared to the 10th power. All right, so just think about breaking 100 up into some of its factors, 10 squared, which turns out to be 10. Remember what we do with those exponents? We bring them down, so I have 10 to the 20th power. And this becomes 10 is 2 times 5. So when you think back to your exponent properties, writing 2 times 5 to the 20th, you just 2 times 5 times 2 times 5, 20 times, you're going to end with 2 to the 20th times 5 to the 20th. And that right there is your prime factorization. Let's see, your greatest prime you have to do to test whether another number is prime. That was where the squares, the prime number squared, worked out really nicely. So p squared was less than or equal to your number. So if you're kind of reverse solving this, the prime that you want to check in a sense would be the square root. So if you check the square root of 769, let me grab my calculator and because yeah, I'm not doing that one mentally. Let's see here. So square root of, let's see here, 769, take the square root. Oops, my calculator makes me do the square root first. Okay, so if I do the square root of 769, this is approximately 27.73. So now notice we don't check 27. 27 is not a prime number. So 26, no. 25, no. 24, no. So I would round this down and say 23. So if I had to check all the primes, I would need to check 2, 3, 5, 7, 11, 13, 17, 19, and 23. These would be all the things I'd have to test to see if 769 is prime. But that's still a lot better than thinking of checking 2, then 3, then 4, then 5, then 6, then 7, then 8, and going all the way up to 769. So instead of checking 769 numbers, we check 1, 2, 3, 4, 5, 6, 7, 8, 9. We only have to check 9 numbers. That's pretty good if you were just trying to check to see if something was prime. Now, some of these we could test, like if I was really doing this in the real world, I would test to see, I can see it's not divisible by 2, just by the last digit. That means it's also not divisible by 5, because 5 does not go in there. 3, if I add the digits, 7 plus 6 is 13, plus 9 is 22. So no, 3 does not work. 11, check the opposites there. 9 plus 7 is 16, but take away 6 is 10. So that one's out. So I'm using those divisibility tests, and I've already ruled out 4 right away. It leaves only 5 numbers for me to check to know whether this is actually prime. And 769 is 700 plus 69. And I got to tell you, that's 700 plus 70 minus 1 is what that really is. And 7 works here and here, but it does not work there. So 7 is out as well. So we've already ruled out quite a few different numbers. There's really only 4 you'd have to check. And that can make it a lot quicker to tell whether larger numbers are prime. Pretty cool. Same kind of thing up here. Determine whether the following are prime. I would take the square root of this and just actually check the primes. So for example, if I was checking the number 119, I'm not going to do all of these. There's quite a few, but I want you to get some practice in there as well. So 119, I would take the square root of 119. And then again, grab my calculator for that because I don't have that one memorized. Let's see here, square root of 119. And gotta tip my calculator sideways. Let's see, raised 5. So it's 10.98. Okay, so about 10.98. So I go to the next prime number down from this. So think about it. The number below 10.98 would be 10, but that's not prime. 9, nope. 8, nope. 7. So really all I have to do is check 2, 3, 5, and 7, and that might work. Let's see, your last digit is a 9. That rules out 2 and 5. Add them up. 9 plus 1 is 10 plus 1 is 11. So 3 doesn't work. And the last thing is 7. So 119, break it down into 70 plus 49 because a 70 helps me, makes it smaller. I know it works for 70. And 7 goes into 49. Oh, perfect. So that works out really nicely. So yeah, 7 does go in here. So this would not be a prime. And let's see here, 70 is 10 times 7. 49 is 7 times 7. So we're actually looking at 7 times 17. So it is not prime, and you can actually write out what it is. Let's see your fundamental theorem of arithmetic to justify if 2 divides n and 3 divides n, then 6 divides n. So that is 100% correct because the fundamental theorem of arithmetic says there's exactly one way to write the primes. So if 2 does fit into that number and 3 does fit into that number, then 2 times 3 has to fit into that number. If 4 and 25, again, yeah, there's no factors in common, so 100 would absolutely have to divide that number. Is it always true that if A divides n and B divides n, then AB divides n squared? Ooh, that's interesting. That is interesting. Well, you could take a look, right? We know A divides n, which means what? N is equal to A times something. I'll call it X. We know B divides n. Okay, so now n is also equal to B times, I don't know, Y. And now if we multiply these together, I get n squared, n times n. And on the other side, I get A times B times X times Y. So take a look here. A times something gets you n squared. So yeah, actually we were looking AB. I actually have AB right here. AB multiplied by some whole number, and it gets me n squared. So yeah, that's looking solid. That's looking super good. Absolutely, it's going to work. Okay, find prime factorization of each of the following. Okay, so again, it's very similar to what you did in question 3. The numbers do look a little bit bigger, but use those properties of exponents, right? And if you can, factor. So let me do one of those, which is probably the one that will help the most. Okay, so I'm going to do part C. And that's just because I have done all of these problems and I know part C is usually the one that gives students trouble. So 2 times 3 to the 4th times 5 to the 110 power times 7 plus 4 times 3 to the 4th times 5 to the 110 power. You do not want to multiply this out on your calculator. All right, the number is going to be massive. Right? So what we can do is look for common factors so we can use the distributive property. So here's a 3 to the 4th, so that's common. Here's a 5 to the 110, that's common. And then I see a 2 and a 4, but if I rewrote the 4 as 2 times 2, then the 2 would be common as well. So let's pull everything out that we can. 2 times 3 to the 4th times 5 to the 110, and let's see what remains. Okay, so gone, gone, gone. What's left here is a 7. Okay, now the 2 came out, the 3 to the 4th, the 5 to this. What's left here is a 2. So I have 7 plus 2. Okay, so now I have 2 times 3 to the 4th times 5 to the 110 times the number 9. It wants the prime factorization, though, and 9 is not prime. So think to yourself, wait a minute, 9, that's 3 squared. Got it. but I have some threes and I have some other threes. Just combine them with your properties of exponents, and we are done. Happy face with upward slanted eyebrows. Very happy face. All right. So that's pretty cool. Love those. Don't forget about those. Properties of exponents are there to help you. They are absolutely there to be your friend. Explain why this is not a prime factorization. Hint, hint, hint. Prime factorizations should be prime. So remember that. And let's see here. Is it possible to find non-zero numbers that make this true? If you could find non-zero numbers, there would be like a group of threes over here and like a group of eights and a group of fives. But if you picture it, if that's true, then 3 would have to divide some power of 8. And if it's a power of 8, it would have to divide 8, and 3 does not divide 8. So we'd have a reason why that is not the case. Okay. Let's see here. If this is this a factor of that? Picture. Is there something you can multiply the first one by to get to the second? That's what it means to be a factor. Let's see here. Word problems. I guess sometimes people get kind of stuck on word problems. So I'll do I guess we'll do an egg basket one here, and then we'll call it good. We'll wrap this video up. Okay. So a woman with a basket of eggs finds that if she removes the eggs from the basket 3 or 5 at a time, there's always 1 egg left. Okay. However, if she removes the eggs 7 at a time, there are no eggs left. Okay, so we're getting clues, right? We're getting clues to solve this problem. And if the basket holds up to 100 eggs, how many eggs does she have left? All right, well, now we could just guess and check. Well, let's see if we can make some patterns here. I really like making patterns. First off, if she pulls them out 3 or 5 at a time, there's always 1 egg left. So that means our sequence is not a multiple of 3 or 5 because there's always a remainder. So that means our sequence has to look something like this, the possible number of eggs, 3n plus 1. So we could have a sequence that looks like that, and a second sequence, because also when she pulls them out 5 at a time, there's 1 egg left. So these have to work together. So 3n plus 1 could be 1, could be 4, could be 7, could be 10, right? Because again, if she pulls out 3 at a time, there's 1 left over. Okay, so 13, 16, 19, right? So far, so good. 22, right? 25, 28. What do I want to do here? 31, dot, 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 dot. Okay, so we could keep going, right? We go all the way up to 100. Okay. All right, let's keep going. Now do the one with 5. So now 5n plus 1 would be a 1, a 6, an 11, 16, 21, 26, 31, 36. Again, I'm going up by 5 each time, so that's a little bit quicker and easier to do than the threes. 41, 46, dot, dot, dot. And what I want you to see is there is a pattern here. If you look at, in order for these both to work, right? Even though the number 4 works for the statement about 3, it doesn't work for the statement about 5. So 4 is out, 7 is out, 10 is out, 13 is out, but 16, that's in both lists. So 16 is a possible number of eggs right now. I guess so is the number 1. That's possible. But 6 is not on the other list. So those are out. So I'm looking for things that have to be on both lists. 21 is out. This is out. The next one that matches. Oh, there we go. 31 is on both lists. All of these are out. All of these are out. So, look at what numbers appear on both lists, right? A 1, a 16, a 31. The next number that works would be 46. You might notice that you skip 2 and then hit, skip 2 and then hit, skip 2 and then hit. Whereas on the top, I skip 1, 2, 3, 4, and I skip and then I hit. So I skip 4 and then I hit. So it's the fifth one on top. 1, 2, 3, 4, 5 again. And that's not a coincidence. It took us 5 to find a hit on top. There's a 5. And down here on the bottom, it took us every 3 to get a hit. Coincidence? I think not. So what we can see is for this sequence, we could combine them and say, forget about the 3 and the 5. We really need a sequence that is multiples of 15, and we're just one bigger than that. And that'll take care of both of these in one swoop right away. Okay. Now there's one more condition though. It says, but if I remove 7 eggs at a time, there is nothing left over. Well, 7 eggs at a time is a multiple of 7. So what I need now is this beautiful sequence we just made. I need to look for what in this sequence is multiples of 7, and that'll do it. Okay. So what I'm going to do is I'm just going to keep adding 15. Now, remember, it's 15 times n plus 1. So what I sometimes do when I'm doing these problems is I'll make my 15s because those are easier to just do 15s. And then at the end, I'll just add 1 all at once. 60, 75, 90, and that's it, right? Because it only holds up to 100 eggs. The next one would be 105, and that's out. Okay, so basically I'm adding a 10 and then throw a 5 on there. Then I add 1 to each of these, so it becomes 1, 16, 31, 46, 61, 76, 91. Those are the options. And I need something that's a multiple of 7. So that means 1 is out, 16 is out, 31 is out, 46. Nope. 9 times 7 would be 63. This right here would be 70 plus 6. It works, it doesn't work. And if it didn't work on one of them, it's out. That's theorem 4-2b. And then 91, let's see here. What could I break that down into? Let's get a 70 because I'm looking for multiples of 7. 70 plus 21. Yes, it works. It works. Aha. How many eggs does she have? She has 91 eggs. And if she takes out groups of 3, there's 1 left over. If she takes out groups of 5, there's 1 left over. But if she takes out groups of 7, there's nothing left over. And also, this woman needs a serious pastime, right? Like, seriously. But she's also maybe very interested in math. All right, that wraps it up for this one. Hope that helps out. Have a good rest of your night. Off you go.